Hello and welcome to today's video lesson where we're going to look at icebox calculations for an equilibrium problem. So I chose a fairly simple question. If you want to see a more complicated one, please let me know in the comments. There are so many variations of icebox problems, but this is a relatively simple one. So the question is, I'm given 5 moles of hydrogen and carbon dioxide. They're injected into a 2-liter flask. And it tells me that the hydrogen concentration at equilibrium is 1.1 moles per liter. And the question is to calculate K, so to find the equilibrium constant for this reaction. So you may remember from class that K, it's an equilibrium constant, and its formula will always be your concentration of products. So in this case, my product is water vapor and carbon monoxide. Those are both gases, which, by the way, we can actually take a concentration of gases as well as aqueous reactants and products. Now, they're raised to their mole ratio. In this case, they're both 1, so their exponents are 1, which you don't have to write down. I'm just going to put that there just for a visual. So it's the concentration of the products divided by the concentration of reactants raised to their mole ratio, which again is also 1. So this is the formula I'm going to use to find my equilibrium constant, but we have to be very careful, okay? These concentrations of products and reactants, they have to be at equilibrium, hence the equilibrium constant. So we cannot just put in any random concentrations. We need to know how much of everything we have when the reaction reaches equilibrium. So how are we supposed to do that? Well, I know a little bit of information about the hydrogen at equilibrium, but I don't know anything else. So I'm going to use an icebox or an ice chart to figure out my solution. So ICE stands for initial change in equilibrium. So initial concentration and equilibrium, this is actually what I want, the equilibrium concentrations. That's remember what I'm going to have to plug into my K formula. So if I go to my equation initially, if I go to the products, now it doesn't tell me anything about the products here. We can assume that at the very start of a reaction, products have a concentration of 0 moles per liter because the reaction hasn't really started yet, right? Now, initially, the hydrogen and carbon dioxide, it tells me there's 5 moles injected into a 2-liter flask. Now, again, these are concentrations we're dealing with, so we do need to use our formula, concentration equals moles divided by volume, to change these values into concentrations. These values up here, this represents your initial amount, because you have to read between the lines, right? If it's injected into a flask, that means you're putting them into, this container to react initially. So 5 moles divided by 2 liters, that will be 2.5 moles per liter, or I'll just use capital M. That's the initial reactants I have. Okay, now under change of concentration, we know that reactants will always decrease, right? Because they get consumed. So we're going to say minus X for both of my reactants, which, by the way, we have to think about stoichiometry. So our reactants and products, they will decrease and increase by their mole ratio. Okay, so in this case, this is a 1-to-1 to 1-to-1 mole ratio. They will change proportionally to how many moles you have. So it's just minus 1x or x for my 2 reactants. Now, products, on the other hand, they always get formed during a reaction, right? So the change of products will be plus x or plus 1x. They'll change by their mole ratio. So at equilibrium, my 2 reactants will be actually the same for this question. It'll be 2.5 minus x for the H2 as well as the CO2. This is how much I'm going to have at equilibrium. And then for my products, water and CO, both gases, they will have a equilibrium concentration of 0 plus x. So in this case, it'll just be x. This, again, these are the values I need to find in my icebox so that I can plug them into my equilibrium formula up there to solve this question, which is to calculate K. Okay? So how are we going to do that? So there is some additional information in the question we can use. It tells me that hydrogen's concentration at equilibrium is 1.1 moles per liter. So I know hydrogen has an amount of 1.1 m at equilibrium. I can use that to solve my x value. So let's do some work underneath. We're going to say that at equilibrium, I know that H2 gas equals 1.1 moles per liter. I know that H2 gas started at 2.5 moles per liter. It decreased by a certain amount. And actually, let me clean up my math a little bit. So I'll get rid of that equal sign. So my hydrogen started at 2.5 moles per liter. It decreased by a certain amount. and then by equilibrium, it reached 1.1 moles per liter. So if I do a little bit of algebra and I can say that X will equal 1.4 moles per liter. That's my X value. That's really helpful because what I can do now is take my X value and plug it back into my ice box for both the carbon dioxide as well as the water vapor as well as the CO. I can plug my X value back in to figure out all of the rest of my equilibrium concentrations. So if we go ahead and do that, X is 1.4. So for the carbon dioxide, 2.5 minus 1.4, that's also going to equal 1.1 moles per liter. Again, this is a 1-to-1 mole ratio, so that does make sense. And on the product side, it's 0 plus X, so X is just 1.4 m, so that means I have 1.4 moles per liter of each product as well. So now that I know my equilibrium concentrations of everything, we're going to plug that into our K formula. So I'll just rewrite the formula. K equals your concentration of products. Now, just be careful. This is water vapor, so we can take the concentration of that. And when you get to acid-base problems, you'll get water as a liquid, and we don't actually include that in our K calculation, so we do need to look at the states, okay, of these questions carefully. Okay, so K equals H2O times CO divided by H2 times CO2. K will equal H2O is 1.4 moles per liter. This is, remember, at equilibrium. CO is 1.4 m at equilibrium, divided by H2 and CO, which are both 1.1 moles per liter. Sorry, 1.1 moles per liter. Now the units will cancel out. And K, by the way, even if the units don't cancel perfectly, the equilibrium constant, it will be a unitless quantity, just because it is just describing the ratio. So I'll get a value here of 1.6. If I round it to 2 sig digs, 1.6 is my value for K. Now, what does this answer mean? My answer, we do need to evaluate the magnitude of our answer. So we can say that because K is greater than, it's very close to 1, but because K is a little bit greater than 1, what this means is that at equilibrium, we favor the products. So we're going to say that we have products are favored at equilibrium, which just means we have more products when the reaction goes to equilibrium. We have slightly more products. You can tell from these answers that the values are very close, but we do have slightly more products. So that's how we answer a simple icebox question. If you want to see a more complicated one where the algebra is a little bit more difficult, for example, we have to use the quadratic formula sometimes, and then there are some questions where we have to make some assumptions sometimes as well. So if you want to see a more challenging one, please let me know in the comments. Thanks for tuning in, and good luck with your chemistry studies.